Well, hi everyone, and welcome back to The Experts Debunk the Flat Earth. Today we're going to tackle the Black Swan and other issues related to we see too far for the Earth to be a globe. So let's cue up the music and you can join myself, Wolfie6020, Charlie, and Blue Marble Science as we talk about do we see too far? Well, our next one is one of my personal favorites. We see too far. So, Harry, how far should we see on a flat Earth?
We should see, well, on a flat Earth, what would stop you from seeing to infinity?
Well, I talked to an astronomer a little bit earlier today.
From the point of view of astronomy, there's the thing that's referred to as optical density, which has to do with how much dust and dirt there is between you and the object you're looking at. And that's usually the only limitation of how far you see, is whether there's something in the way. As long as the air is clear enough, you'd have no trouble at all seeing a plane 50 miles away, as long as it was above the horizon.
And there is a dirtiness to the atmosphere, dust, water vapor, things like that, haze mostly. And, we've all seen it. It kind of sits 1,000 feet off the ground. Yeah. The lower 1,000 feet's a little foggy, a little hazy looking. But I asked him specifically, well, if we look straight out over the horizon, how far should we be able to see through this haze? Should we be able to see something 50 miles away? And he goes, easily. And then he brought up the fact that we can easily see the moon halfway down the horizon on the ocean, and we can see a very clear border between the side of the moon and the water.
The reality is that, I can go out and watch the moon set on the Pacific, and I can see the moon set. It clearly sets, it clearly is bisected by the horizon, the water, essentially, as it sets. And the same is true for stars, which are very faint, and I can see them. Now, when the moon sets for me, it's essentially directly overhead somebody that's a quarter of the way around the Earth. Several thousand miles, that moon is directly above them, and yet I'm watching it set. It would have to be at least several thousand miles away, and I can see it. So what are you going to do?
How far away does it have to be before it appears, due to perspective, to touch the water? And is the bottom part of the moon that we can't see any farther away than the top part that we can? Why shouldn't we be able to see the Sears Tower in Chicago from the shores of Lake Michigan 60 miles away over the beautiful air above Lake Michigan? There's no reason at all we shouldn't be able to see that due to atmospheric blockage. Why is it we don't see that on a regular day all the way down to Lakeshore Drive?
Well, because the Earth isn't flat to begin with.
Yeah, well, that's kind of obvious. Yeah, it's kind of curvy.
That's the first problem.
Mm-hmm.
And yeah, you do see the moon looking out over the horizon that we're familiar with. Would you see that on a flat Earth? Well, no, you wouldn't in the first place. The moon would never get down there, I don't think. How would it? It's supposed to be, 3,000 miles, 3,500 miles up. That's what they tell us. They think it is. And how far away from you can it possibly ever be? Supposedly.
Yeah.
9,000 miles, maybe. The angle never gets you down to anywhere close to the horizon.
So in other words, if the moon was about 3,500 miles high, and it was, say, 20,000 miles away, we could actually draw a triangle on a flat Earth, couldn't we?
Yeah, you could.
And that angle would not be zero.
No, it's not. Not even close.
All right.
Not even close.
Now,
nothing geometrically works out on the flat Earth.
Well, it's a good thing they don't like math, so they don't know geometry. All right, so theoretically, on a flat Earth, if we looked out and saw a horizon, that would be pretty much at our eye level, wouldn't it be?
It could never be at your eye level.
But would it be close?
You know, Bob, I don't think so. And here's why I say that. If you think about this on a flat Earth, how far is Earth, how much Earth is out in front of us? Unless you're looking due south and you're getting close to that supposed ice wall of theirs, how far can you possibly think that you would ever be able to see and to begin with? No matter what, you know, it's the old parallel lines don't intersect, right? That flat horizon can never quite rise to your eye level. It may get close,
Yeah.
but it can't ever come all the way up to your eye level.
Well, if you're 6 feet tall and you're looking out at her horizon 10,000 miles away, the drop to the horizon is going to be about as close to zero as you can get and not be zero, right?
Yeah.
So it would
close.
be kind of close to your eye level. Now, when we got out there, if we started looking at things, we'd start running into problems with the Rowley criterion, right?
Yeah, pretty quickly you would.
And the Rowley criterion is based on the frequency of light. So what you would have would be, you know, the aperture of your eye isn't changing, but the frequency of light in white light, you've got red, blue, and green and everything in the white light. Each one of those has a slightly different frequency. So instead of being a sharp, crisp line, the horizon would actually have depth based on the color, wouldn't it?
It should.
So it would be fuzzy. How could we possibly see a sharp horizon on a flat Earth?
Yeah, that's exactly the point I've been making to these guys time and time again. You cannot possibly see a sharp, crisp, clear horizon on a flat Earth. It cannot happen.
And I can't really think of how it could possibly drop from the horizontal, and we've clearly measured it dropping from the horizontal on a flat Earth.
Well, there's another problem.
What's that?
On a flat Earth, the horizon can never be in front of any object. If you could see the horizon on a flat Earth, it could not possibly be or appear to be in front of any object.
Yet
all the time we see horizons, very crisp, pristine, clear horizons in obscuring and in front of things. That is simply not possible on a flat Earth.
Yeah, I think you're right on that. I definitely think you're right on that. And it's just one of those things I think they haven't thought out very well. You know, they're making a lot of hay right now about something they're calling the Black Swan, which personally I find amusing because it's not a black swan and they're not even using it correctly.
I agree. Yeah.
What are your thoughts on the Black Swan? How far should we see, and what's seeing too far?
What's seeing too far? Well, my throwback to them is, why don't we have any photographs of the sun setting behind the mountains of Hawaii from 200 miles away on a cruise ship? We don't have anything like that. And if you notice, the flat earthers, they're always showing us these observations over very tiny distances. And when calculated properly, factoring in refraction, they fit the globe every single time. That Black Swan observation, I think you can discount it straight away just by the very obvious distortion and by the fact that other photographs of those two objects in the water show very different results on different days. And on most occasions, it's very obvious that the far one is at a lower position and the base of it is hidden behind the horizon. So, yeah, the Black Swan is they've just cherry-picked a day with extreme refraction and they're just not letting it go, even though it has been debunked many times.
Yeah, I think you've done it. I've done it. Blue Marble Science has done it. Mm-hmm. You know, it's kind of a fun way to demonstrate what refraction is.
Yeah, absolutely. Now, I mean, with my astronomy, you know, I have done a lot of sunsets and moon sets, and it's quite interesting when you're tracking the sun precisely all day and it just doesn't move in the frame of the telescope. But as it gets closer to the horizon, you do see it moving. It's because the refraction is lifting it up. So even though the telescope is continuing to move at that very precise 15 degrees per hour, there's just a half a degree or 1 degree of refraction just raising the sun up. So I actually have a video on that where you see the sun just moving in the frame. And most of the time I'll do a manual correction, just a very slight correction. And that'll just keep the sun framed in the center. But yeah, you can absolutely see the refraction. In fact, some telescopes have a tracking rate called the King rate. Are you familiar with that one, Bob?
Not a bit.
Okay. Sidereal rate is to track the stars. We've got solar rate, which is to track the sun. That's a precise 15 degrees per hour. But the King rate will basically track at sidereal rate, plus it will allow for average refraction once it gets close to the horizon. It's quite good. I do have a little telescope that uses that, but I've never actually used it myself. But King rate tracking in a telescope factors in the refraction.
That's actually a very interesting point and something that I wouldn't mind doing a video on one of these days.
Mm-hmm. Yes.
The refraction becomes important as you get down to 5 or 10 degrees to the horizon.
Yes.
And that actually causes the sun to either rise up or lag behind. So it kind of hovers right there at the horizon. What about this talk about change in angular size? I understand that with a good solar filter, the sun doesn't really change in angular size. Is that right?
No, it doesn't. And I've done a lot of work on that with proper solar filters, various different types. In fact, that is what got me into astronomy. I wanted to go and just buy a very basic solar filter for my P900. And there's a great shop, a great telescope shop in Glebe in Sydney, near the city, and it's called Bintel. And I walked in there, I looked online, and they had the solar filters for my camera, and I walked in there, and they've got a beautiful showroom of all these high-end equatorial mounts and telescopes. And I remember within 3 seconds of walking in this shop, I thought, oh, this is going to be dangerous. So I bought my solar filter and I went home and I was happy with that. But I just had to go back a couple of weeks later and just buy a telescope. And that's how I got into it.
You knew that the bug had you, huh?
I could tell straight away. As soon as I see cool devices like that, I thought, I've got to have one.
Well, thank you very much for stopping by today, and I hope that this helped you out when flat earthers tell you we see too far for it to be a globe. Because the bottom line is, if you see it on Earth, you can see that on a globe. We just have to figure out exactly what's going on to allow us to see something that we wouldn't normally expect. In our next episode, we'll continue The Experts Debunk the Flat Earth. In the meantime, hit that like and subscribe button down there. I'd love to have you as a member of the channel, and there's a link to memberships right in the description. And make sure you check out my new channel, Common Sense Science. So in the meantime, this is Bob the Science Guy, signing out from Northern Michigan. Thank you again for stopping by, and we'll see you again soon.